if a heat shield fails, the problem is not abstract, it is structural. A vehicle coming back through an atmosphere depends on material that can survive heat, gas release, and stress at the same time. NASA's new report looks at one failure mode in detailed spallation, where fragments suddenly break away from thermal protection material. The reason to care now is simple. Reentry systems are central to modern spaceflight, and engineers need to know not just that a material fails, but how it starts failing from inside. This study tries to connect chemistry to mechanics. It looks at what gases are released during heating, how pressure builds below the surface, and when that pressure may exceed the material's strength. That gives a clearer picture of risk during extreme entry conditions. The core question is what happens beneath the surface of a thermal protection system when it faces a high enthalpy environment. NASA says the issue is internal pressure buildup. As the material heats, gases evolve, move through the structure, and interact with its microstructure. That sounds small scale, but it matters because internal gas pressure can create cracks and trigger larger instability. The report focuses on how those subsurface processes may lead to spallation. In plain terms, the material does not just burn from the outside. It changes internally as temperature rises. Different gases appear at different stages. Permeability matters too, because gas trapped in a less permeable material has fewer ways to escape. So the study is really about timing when gases are released, where they collect, and whether the structure is still strong enough to contain the pressure. NASA used complementary approaches. In the Hypersonic Materials Environmental Test System, or HIMETS, researchers measured pressure inside the material during testing. That gave a direct view of how subsurface pressure changed as heating progressed. Then they used mass spectrometry to identify the volatile species released as the material decomposed. This second method helps separate lower temperature releases from higher temperature breakdown products. The report highlights one important distinction. Water can esper early, before major changes in permeability. Later, as the polymer backbone breaks down through pyrolysis, much more gas is produced. Put together, these methods linked chemical decomposition to mechanical response. That is the practical value of the study. It did not only observe damage after the fact. It tried to map the sequence from gas generation to pressure rise to structural instability inside the thermal protection material. The report describes a likely sequence. First comes initial heating. At that stage, absorbed water is released from microballoons in the surrounding matrix before extensive pyrolysis begins. NASA says even this small amount of early water release can matter, because the material may still have low permeability. If gas cannot move out easily, localized stresses can develop and small cracks may form. Then the process intensifies. As heating continues, the pyrolysis front moves forward and releases a much larger amount of gas. Pressure rises rapidly below the surface. If that internal pressure becomes greater than the local strength of the material, fragments can eject suddenly. That is the spallation event. So the report points to an interplay, not a single cause, early volatile release. Later pyrolysis gas production, gas transport limits, and local strength together shape whether the material stays intact or breaks apart. The clearest contribution is not a dramatic new claim. It is a more grounded mechanism. NAS, as the combined data, establish a quantitative link between chemical decomposition and mechanical response. That matters because it helps explain how micro-scale chemical changes can become macro-scale instability. For engineers, that can improve interpretation of degradation and failure modes and thermal protection systems under entry conditions. It also sharpens attention on a stage that might otherwise see minor early water release before extensive pyrolysis. The source does not claim to solve every heat shield problem. It offers a better foundation for understanding one path to failure. That makes the study useful in a measured way. If you want safer reentry materials, you need to know when gases form, how pressure builds, and why a surface can suddenly shed pieces even before total material breakdown.